Up until this point, what we have discussed might be called the microscopic laws or Maxwell's equations. And what we mean by this is that we have assumed, and when we write down Maxwell's equations, let's just write them down again. So we have del value is 4 pi rho, del that v equals 0, del cross v minus 1 over c dt, del cross v 4 pi over c j plus 1 over c dt. So when we write this down, we're assuming that we know absolutely all of the charge density everywhere and all of the current density everywhere. So, for example, suppose, we do we make a capacitor here. We want to know, what is the electric fields and magnetic fields in this room. Well, are we really going to model the charge density in every molecule in the air when we do that? No, we're not. That's not typically necessary to do, because we're looking at a situation where we sometimes are interested in the macroscopic phenomena. And so all of the very strongly varying charge distributions associated with molecular orbitals in nitrogen and air are not going to be relevant to thinking about what the electric field is in a capacitor in air. There's some sense when we're talking about macroscopic phenomena that what we want to do is average over microscopic variations. So we can get at this in a fairly straightforward way by a process of what you might call coarse graining. That is to say, here's whatever our region we're interested in. There's lots of microscopic molecules, atoms, what have you. And instead of thinking about a point in the space where we might have variation, very strong variations in, say, the charge density over angstrom scales, nanometer scales, we think about coarse graining averaging over some grains that are fairly coarse, hence the name coarse graining, okay? And so, there might be something like, 1/10 of Avogadro's number of molecules inside this coarse grain, and we think about that as that coarse grain as the new point in the distribution. Okay, so coarse graining means we're going to average over scales large compared to microscopic scales. But tiny compared to the relevant macroscopic scale. Now, that of course is a fairly qualitative thing. What we consider to be macroscopic will depend on the problem at hand. But there's certainly going to be plenty of room. I mean, maybe this is microns. Okay? Maybe it's 100 nanometers. Still, there's plenty of room above and where we could call this a coarse grain. So exactly where the cutoff is not, this is not sharp. It will really depend on the problem at hand, but there's plenty of room between the microscopic and the macroscopic scales. Okay? So, in that circumstance, what we would say is that, well, the macroscopic charge density is a function of some coarse-grained position. Would be, we have some coarse-graining function. We might formally write it in the following way. So this function at every point in the microscopic distribution is some weighting function. So it would be centered at some point x prime. I have some function. If it was an absolute fine grain, this would be a delta function. But as a coarse grain, it has some width, which is the coarse graining scale. Maybe some tens of angstroms. So, what one can show with a little work that I don't feel like doing because it's not so important, is that if I coarse grain everything, all the fields now, so now I have macroscopic electric fields. If I look at the say the divergence of the coarse-grained electric field, coarse-grained over the same scale, it's given by the same kind of Maxwell's equations that we had before, where now these are the coarse-grained sources. Okay? So, what we're going to study today, I'm sure this is something everyone should have seen in their, at some level in their undergraduate courses, is the writing down the macroscopic Maxwell's equations. What's different? Well, we typically, when we think about these kinds of macroscopic equations, we typically divide up the sources as, in this case, the sources that are bound up in the microscopic constituents, the so-called bound charge. So this would be, say, the charges that are bound in the molecules that make up the microscopic environment in which we are looking at electromagnetic phenomena. And then whatever excess charge, maybe this is the charge on the capacitor, or maybe there's some, plasma, there's some ionized stuff out there, the so-called free charge. This is the charge not bound. This is the bound in the molecules, and this is the free charge. Okay, so when we want to deal with the bound charge density is the stuff of which there's lots of, truly, if we wanted to take into account, we could do this in the fine grained sense, the bound charge is a complicated thing. And the whole point here now is to, through this coarse graining, simplify the description of this bound charge in some way. So, if this charge density is bound, so let's look at the bound charge So, you know, we have some nucleus for some particular, you know, so we have some electron cloud. Then on the coarse-grained scale, if we're not looking inside the molecule or atom, then the thing is neutral if it's bound in this way. So we can ignore, in thinking about the bound charge density, the monopole contribution, electric monopole contribution to the bound charge is 0, because it's bound, it's neutral. So the first possible dominant contribution to the bound charge density is electric dipolar.
Yes? So with the bound charge, I mean, could you also say that basically, like, even if we did have some sort of ion that wasn't neutral, I mean, we would just lump that into the free charge
We
anyway?
would, indeed.
Okay.
So the way we do this division, we'd say that would constitute one of the contributions to the, we would then coarse grain over all those ions, and that would constitute part of the free charge. So the bound, by convention, we put the bound charge as all of, we lump that in as all of the neutral part.
Okay.
That's by convention.
Okay.
And then anything else that's charged as a finite monopole is coarse grained and put into the free.
Okay.
Okay, so the key player then in thinking about the source of the neutral bound charge is not really charge density, but dipole density, electric dipole density, because that's the dominant term. If maybe that's 0 too, but at least that's the first, would be the first possible non-zero contribution. So for neutral, I'll emphasize that point because Jacob makes a good point, neutral bound charges, we deal with what we call the electric dipole density. Which we call capital P as a function of position and time. So this is equal to the sum over all the microscopic dipoles, our coarse grained function at the position of the dipole, the strength of the dipole at position N. So this is a dot, remember this coarse graining function is a density, so this has the units of electric dipole per unit volume. Okay? And it's given a very confusing name. It's also called the polarization. It has nothing to do with the polarization of a wave. It's called the polarization for reasons I will explain a bit later. That's why it's called P. All right? It's capital P. All right, so if we had such a, so let's think about this picture again. I'll draw it over here. Here's some chunk of material. Here's, I want to know, what is at some point here, if there's some possible P is a function, let's call the source points x prime, and the position of observation x, and we have our usual script dr, x minus x prime. I want to know what is, for example, what is the electric potential for such a source? Well, it's a superposition of all the dipolar potentials from each coarse grain. And we know, because we remember what the dipole potential is, right? If I have a dipole, let's call there's a little dp here, which is p of x prime d cubed x prime. That's my differential. Oh, I'm sorry about my horrible handwriting. Let me just write it over here so we can see a little bit better. There's a little dp here, which is big P at position x prime d cubed x prime. Given a dp, what is the d phi? It's proportional to dp. And how does it go with script dr and all of that? Goes like 1 over something.
1 over something, right?
So how fast does the potential fall off with this? Didn't know what you're talking about. 1 over r squared, so that's good. It's kind of 1 over r squared. And it's in the direction of the dipole, right? So the full potential, if I integrate, and this is equal, I can write it out, p x prime d cubed x prime, and script dr here, that's equivalent to the gradient minus the gradient of 1 over r. That's another way of writing it, right? Because that's the gradient minus the gradient of 1 over r is that function. That's like the focal point charge, which is equal to minus p x prime d cubed x out front, p and x prime t dotted into the gradient 1 over x minus x prime. And now I'll play a trick. The gradient of this with respect to x is minus the gradient of this with respect to the prime variable. So I'll change that to a plus. So what we have thus is the total potential integrated over all the fine grains, all the coarse grains, pardon me. Can be written as such. Can be written over the volume of where the sources are. And now we do our favorite integration by parts. Integration by parts means throw the derivative onto the other side with the minus sign. Yes?
What happened to the time dependence?
It's in there. You just didn't write it.
So is time dependence just removed from the potential?
No, it's in there too. It's a quads. It's in their field here. We're talking about the statics, but it's all at the same time, indeed. So what can we say? So now we're going to do integration by parts, and so I get the surface term. And then I get the term where I put the derivative on the other side. So what can we say about this? Well, suppose I had, what is the form of this remind us of? Suppose I had, recall the microscopic laws, when we had microscopic electrostatics. If I had some source as a function of position, and I'm just going to say it's all so instantaneously function of time, and I wanted to know what is the microscopic electric potential, how would we write that? It's d cubed over r, right? Which is d cubed x prime, rho to x prime, x minus x prime. That's what we did right at the beginning of the semester, right? So this has exactly that form, and thus we have an interpretation, let's get rid of this little guy, of this thing. We call this the bound charge density, fine and coarse-grained as a function of position at the instantaneous time. So minus the divergence of the polarization, the dipole density is the coarse-grained bound charge density. What about this term? Well, we can, if there is, in this case, you know, if there's some dipoles here in some order, we can see that there's going to also be some bound surface charge density at the surface related to the normal of that surface dotted into the local polarization density if we had some dipoles that were polarized at the surface. Okay. At the moment, let's assume the boundary effects are not relevant to us. We can in principle take them into account as lumping them into the bound charge density with an appropriate delta function at the surface. And then that would just pick off this term if we wanted to. Okay, so with this expression, this important relationship between the bound charge density and the polarization, we can look at the macroscopic Gauss's law. It says that we had, now I'm not going to put the term macro in here. I'm looking at the macroscopic electric field, which we said was the sum of the free charge and the bound charge. But the bound charge was equal to minus the divergence of the polarization. And thus, the combination E plus, and these lovely units, 4 pi P, is equal to 4 pi rho free. And as you remember, this combination, maybe not with this set of units, but this set of this combination of the electric field and the local polarization density or dipole density is known as the displacement field. D, as a function of position and time, is equal to the local electric field plus 4 pi times the local polarization density. And thus, the macroscopic Gauss's law is del dot E is 4 pi rho free. sources, that is to say the current. For macroscopic magnetic fields. Well, this gets a lot messier, a lot more complicated. Magnetic phenomena are just more complicated. And one of the ways that they're more complicated is, of course, we really want to get into the macroscopic laws of magnetism. We have to worry about spin. Spin isn't really current. But when we're dealing with Maxwell equations, we don't really worry about that. So, you know, in the molecules and whatnot, I can think about, okay, here's my nucleus, you know, I can think, oh, there's some orbit, there's an electron going around, there's some current loop. But of course, this also has a spin vector associated with it. Both of those, in principle, give rise to magnetic phenomena. They're sort of different. This is the reason why materials are both, could be either diamagnetic or paramagnetic. We'll discuss that maybe just a little bit. Nonetheless, the stuff that has to do with, you know, both the spin and the orbits, we call that bound current. Okay? And the bound current is associated with some magnetic dipoles. So in the same way that we define a electric dipole density, we define a coarse-grained magnetic dipole density. And we call that M, function of position and time, is the coarse graining function times whatever the local magnetic dipole moment is for the N contribution. And that capital M, that magnetic dipole density, is known as the magnetization. Okay. So, once again, now I can ask, if I have this chunk of magnetic material, and I want to know, at some, here I am, here's some X prime, here's some dm, which is coarse-grained now, so it's the M, the magnetization in that little coarse grain. And I'm looking at the field over here, and I want to know what is the vector potential associated with this dm. So what is dA? Well, that's the whole integral. A x of t is integral over all these guys, all the dm's. And what's the vector potential of a magnetic dipole? Well, your first guess is it looks just like the electric, because the electric and magnetic, they look, you know, kind of the same, but where there was a dot product, there's a cross product. It would be right. Okay? Everything's got the same units, so that's good. So we can play the same trick that we did before, d cubed x prime and x prime t, now crossed into del prime x prime. And so we can again do our integration by parts, and we get a surface term. plus term. That's the curl of the magnetization.
EM vector on the left.
Where is it? This guy?
The big M. Shouldn't it be
That's a vector, yes, thanks.
here to the left?
Okay, so once again, how we can interpret this similarly to the way that we interpreted the potential in the electric case. There is a bound source of current density and a bound surface current density. If I had a source of current, we know the vector potential is 1 over c j bound x prime. This is the potential associated with that bulk current density. That's what we wrote. It looks just like the scalar potential, but you know, current is charge times speed, so there's the 1 over c there. And then this is k surface cross n hat dA times 1 over the speed of light, x minus x. And thus, just like we had in the electric case, we have actually, there's a slight subtlety here. Let me call it bound magnetic. For reasons that I'll remind you of in a moment. So, what we see here is that the bound magnetic source of current is C times the curl of M, curl of the magnetization. Okay, there's of course, if we want to take into account the boundaries, there is surface current here, which is the cross product with the local noise. Now, why did I do this little flub and made this extra complicated subscript that says this is the bound, the magnetic part of the bound? Because the fact we should note in dynamics there is another possible source of bound current. And that is the fact that our bound charge can be moving around. So if I look at the rate of change of the bound charge density, well, by the conservation of charge, that is equal to minus the divergence of the bound current density due to that charge. And we just wrote what that is. That is equal to minus the divergence of the polarization. And thus, we see that there is another source of bound current density, which if there is a time rate of change of the polarization. This is a very important contribution. In all of optics, this is the most important thing. All this other stuff is garbage. This is all we really care about. This is the polarization. So I'm going to simplify the notation a little bit and call this the polarization current. Just call it pole. And we'll call the other thing the magnetization current. Okay, so now we're ready to write down the macroscopic version of Ampere's law. So now what we have is del cross B is 4 pi over C. There's the free, whatever free current there is, that maybe is floating in copper wires, that's not bound in the microscopic material, plus J mag, plus J pole, plus 1 over C dt. Okay. So let's plug in for these guys. The magnetization current we said was C del cross M. The polarization current is the time rate of change of the polarization, plus 1 over C dt. So now let's combine together all the curls, all the d by dt's, and I get the curl of d minus 4 pi m is equal to 4 pi over c j free plus 1 over c d by dt e plus 4 pi p. Right? And so we end with the following equation. Del cross H is 4 pi over C J free plus 1 over C dB dt, where H is this field. And that field has the name, unfortunately, the magnetic field. Now, in physics, we tend to call this the auxiliary magnetic field. Now, I'll come to this in a little bit. Engineers, electrical engineers, always talk about EH rather than EB. Maybe you've seen that. There's a reason for that. There are sort of two reasons for that. The most important thing is that if you're creating magnetic fields, say you have a solenoid or some current that's creating magnetic field, what you control typically is the free current. So you put a certain amount of current through your wire, and that's what you have control over. So it makes sense, in some sense, to talk about the thing whose source is just the free current. That's one of the reasons that electron engineers like to talk about H rather than B. Whereas in electric phenomena, you typically don't control the amount of free charge. What you do is you put a voltage across some capacitor, say, and then the charge adjusts itself, however it needs to adjust itself, so that it satisfies the boundary conditions. You don't put some free charge with my free charge aerosol That's not what you do. You hook up a battery and the charges come, some are bound, some are free. So you don't typically control. That's why the E field is the more natural thing, because E is related to B. I'm sorry. E is related to the voltage, and H is related to the current. So if you're an electrical engineer and you think about IV relations, that is to say current voltage, you relate E and H are like volts and current. That's why you always see electrical engineers talk about E and H. It's also kind of true that H and E have more similar relations. Note here that H is equal to, I'm sorry, that right, B is equal to H plus 4 pi M. That looks more like D is equal to H plus 4 pi P. So in some sense, the equations look more parallel between E and H and D and B. But physically, the force, the Lorentz force on a charge is due to B, not H. So that's why in physics, we always talk about B as the magnetic field. Okie dokie. So we have now the macroscopic Maxwell equations. Del dot D is 4 pi rho free. Del dot B is 0. Del cross E is minus 1 over 4, I'm sorry, minus 1 over C dt. Faraday's law is unchanged. And del cross H is 4 pi over C J free plus 1 over C dt. Where B is E plus 4 pi P, and H is B minus 4 pi M. Okay. One thing that follows from these laws are the boundary conditions that are important. So, if we have some materials that are defined by different polarization densities and magnetization densities, we can ask, how does the electric and magnetic fields, what continuity equations must be satisfied, assuming some sharp boundary between them? So you remember we did this in the context of the microscopic laws. If the way you do that is you look at either a little contour loop like this, using the curl equations, or a little pillbox using the divergence equations, and you take the limit that you squeeze the contour around the boundary. So this, our lovely pillbox, which they enjoyed in the 18th century, tells us about how the normal contributions to the fields vary across the boundary. And this tells us something about how the tangential components of the field vary across the boundary. And so from this, it follows immediately that the normal component of the displacement is continuous unless there is free charge. If there's free charge, then there can be surface current, surface charge, and it can be discontinuous. And the amount by which is discontinuous, normal to the surface, relates to the free charge density. This, right, so I would say there's some there's a perpendicular component and a parallel component. Okay? So the change across the boundary depends on the amount of free charge. The change in the magnetic field, B, is its normal component doesn't change because that be a 0. The tangential E is continuous, but the tangential H is continuous unless there is free surface current. Note, this doesn't say that the normal E is continuous if this is 0. Suppose the free charge density on the surface were 0. It says the normal component of D would then be continuous, but it doesn't say the normal component of E is continuous. Similarly, this is about H, not B. We'll use those boundary conditions to remind ourselves of them when we look at wave propagation at boundaries. I'm sure you've seen. Okay, what's next? Oh yeah, that's what's next. Where's the board? So, at this point, we haven't said what the dipole density or magnetization density, what they are. Of course, in general, that depends on the details of the material in which we find ourselves. So I might have a magnet, it has some intrinsic magnetization, and it would just be what it is, and you have to calculate it or measure it or something. But sometimes we have, and quite often it's the case, in many cases, P and M are 0 in the absence of an external field. So in air, the dipole density is 0, because on average, all these molecules, all their dipoles are pointing in random directions at thermal temperatures. There's no dipole moment on average in a coarse grain. So the amount of polarization density and magnetization density will depend on applying a field that will polarize or magnetize, the sound hence the name polarization or magnetization. And the relationship between PM and applied E and H, and here we do talk about in terms of H, because H is the sort of the implied field, because it's the thing that comes from the free currents. That relationship are known as the constitutive relations. So, in general, what these relationships are depends on material properties, be they atoms, molecules, clusters, solids. How the material responds to the applied fields depends on the structure of the matter in which you're applying it. But we could say some general things. So for sufficiently weak fields, the response is linear. That is to say, the amount of polarization or the amount of magnetization is just proportional to the amount of field. Of course, if the fields are so big, they start ripping, on the strength of the amount of binding of the electric field inside a hydrogen atom, well, then you're just going to start ionizing. That's not going to be a linear function anymore. But for sufficiently weak fields, it's linear. Of course, when we get into something nonlinear, that's the fun stuff, nonlinear optics, but we're not going there. We're going to stick with linear. So, another thing to say about it is that typically, the response is frequency dependent. Typically it's not, yeah, I would say generally. That is to say, if I have resonant phenomena, if I'm driving my material with an oscillating field, if my oscillating field is near to a natural resonance of the bound charges, then I'm going to get a resonant response. And depending on, and sometimes, for crystals, K dependent. If I were to think about a decomposition of my field in terms of spatial Fourier components, not just temporal Fourier components, then it will depend not just on the magnitude of the K vector, but the direction of the K vector. So a general linear response relationship looks like this. P in the Fourier domain as a function of omega and K is proportional to E in the Fourier domain. And the proportionality we call I, the susceptibility. Now, that susceptibility is a function of omega and K generally. I'll call this the electric susceptibility. Moreover, if I have things like crystals, if I push it in one direction, it doesn't mean that the charges are going to move in that direction because they have strain on them from all their other charges to which they're bound. So most generally, and I know you love this, it's a tensor. Okay? So this is known as the electric susceptibility tensor. It's how susceptible is the system to being polarized given a certain field. Similarly, we get a magnetization, which is generally a function of that. There is a magnetic susceptibility tensor, which is the proportionality by convention to H. Okay? Now, the K dependence is rarer than the omega dependence. That will really depend on some very special crystal structure. So let's assume sufficient homogeneity that the tensors are independent of the K vector, chi . All right. Then we can write the polarization, the induced polarization and the induced magnetization in the time domain by taking the inverse Fourier transform with respect to omega. So when I take the inverse Fourier transform relative to omega, and I got the product of two functions, what does it look like in the time domain?
Convolution.
The convolution. All right. So now this is in the time domain. You know, I really wanted, let's put a little twiddle under this. This is the Fourier domain. This is the time domain dotted into Ex. And similarly for n, but let's just focus on P for the moment. So the fact that the polarization at time t is not proportional to the electric field at the same time, but involves an integral over all times, reflects the fact that there is a finite response time of the material. It's being driven, but it's not instantaneously going to do it. It's got restoring forces and transients, and eventually will come to steady state, perhaps. But there is a response time between the force being applied and the response. If this were a delta function, well then it would be instantaneous response, and then it would just be proportional. Which means in the Fourier domain that the response function is relatively independent of frequency, because an infinitely flat frequency response is a delta function response in time. So to the degree to which we're in a regime where the frequency dependent is fairly flat, then it's a reasonable approximation to take this as instantaneous response. But if we're near a resonance, for example, an absorption resonance, where we would imagine a very strongly varying frequency response, well then that will be a terrible approximation. Okie dokie. So, my little gnome following me around the room, erasing it by lecture. All right, so let's look at the particular case where we have, for the moment, well, let's see, do I need to do that? Now, let me say something more general first. I guess it'll be interesting. So let's consider that for linear response, let's look at what the displacement vector is at a certain time. We said that's E plus 4 pi p, which is E plus 4 pi integral over t prime dotted into, I'm also looking at linear response, no k dependence. Which I can write as the integral over t prime, a vector we call epsilon. Not the polarization, it's a totally different epsilon. Not, yeah, it's a tensor anyway. Where epsilon is equal to the unit tensor times a delta function plus chi of a function. We have 4 pi. This is called the permittivity tensor. In the Fourier domain, as a function of omega, this is equal to 1 plus 4 pi chi, with no. So this is the permittivity tensor. Epsilon naught is the permittivity of free space, where chi is 0. All right, so if we can, for negligible response time, d is equal to epsilon dotted into I should say this in the time domain, let me write it more explicitly. D as a function of position and time is epsilon dotted into E. So this is for a homogeneous medium with no k dependence and for negligible response time. Then D is just proportional to E through the, it's not the permittivity, it's the yes, the permittivity, yeah. Similarly, we have the same kind of relationships for magnetic fields. We have B is equal to H plus the integral chi m dotted into H. Which can be written as mu dotted into H. And mu is known as the permeability. Mu naught is the permeability of free space, which of course is 1. And if I have negligible response time, then B is mu H. So let's return now to this board. And let's look at macroscopic Maxwell's equations when I have linear response. And I'm going to make it the simplest possible case. Homogeneous material. Are scalars. Instantaneous response. So in this case, D is epsilon E, and B is mu H, where epsilon and mu are just scalars. Then we can plug that in to the macroscopic Maxwell equation, where these are just numbers. Not a function of position or time. Let's plug it in. We get then del dot D is 4 pi rho free becomes del dot E is equal to 4 pi rho free over epsilon. Okay? And of course, in free space, it's epsilon naught, which is 1 in these units. Del cross H is 4 pi over C J free plus 1 over C dD dt becomes, well, H is B over mu, and D is epsilon E. So I can multiply everything through by mu, and I get del cross B is equal to 4 pi over C mu J free plus mu times epsilon over C dt. And of course, del dot B is still 0, and del cross E is still minus 1 over C dD dt. Okay, so these are the equations, Maxwell's equations, inside a material where we summarize all the complicated details of all of the bound charges and bound currents in terms of two numbers, epsilon and mu. And typically, mu in, say, most regimes we care about, mu is 1 anyway. And it's only epsilon that has a substantial difference from 1. I should say a few words about units, because you've seen this before, I'm sure, in your undergraduate course. You use SI units, and I want to make certain things clear here. So note, in CGS units, E, B, D, H, P, N, all have the same units. Right? I mean, we just added them together. They better have the same units. There's no epsilon naught here, anything like funny like that. And chi epsilon, or chi e, chi n, epsilon, and mu are dimensionless. That contrasts in SI units, where epsilon and mu have units. And then you typically look at the ratio of epsilon to epsilon naught, or mu to mu naught. We call that either the dielectric constant, something like that. But here, epsilon naught and mu naught are one. They don't have units. So all of these guys are the same units, and these guys are dimensions. All right, final point. We'll have to wait because we don't have enough time to do it. Oh, we have 3 minutes. 3 minutes to do it. iPhone never lies. So, the last thing I want to talk about is energy and momentum. No, I'll just talk about energy in the field for macroscopic Maxwell equations. So, let's begin by recalling, let's think about now minus J free dotted into the electric field is equal to minus the rate at which fields do work on free charges. So that's equal to the rate of creation of electromagnetic energy in macroscopic fields. Okay? So let's look at what that is. According to this equation, let's forget about linear response. Let's talk about the general. J free is equal to C over 4 pi, the curl of H, minus 1 over C ddt. All right, solving that. So that dotted into E, put a minus sign, is equal to minus C over 4 pi del cross H dotted into E plus 1 over 4 pi E dotted into E. Okay. So what does that equal? Well, we can do a little aside over here, and with a little bit of manipulation show that the divergence of the vector E cross H is equal to H dotted into del cross E minus E dotted into del cross H. How do you do it? Write out the tensor notation, repeat it in the C's. I know you love it. So now we can plug in, we have E dotted into del cross H with a minus sign is equal to this minus that. Okay, so this is equal to del dotted into C over 4 pi E cross H plus the minus C over 4 pi E dotted, no, H dotted into del cross E plus 1 over 4 pi E dotted into dt. So the bottom line, which is now the top line, del cross E is minus 1 over C dt. And so the rate of creation of energy is the divergence of C E cross H plus 1 over 4 pi B dotted into E dotted into dt plus H dotted into dt. And this is Poynting's theorem in macroscopic Maxwell equations. So what do we see from this? We see the flux density here. This is the Poynting vector. The Poynting vector S is now E cross H times C over 4 pi, and the rate of change of the energy density depends on not just E squared and B squared, but E and D and B and H. So we'll pick this up next time. All right? Have a good afternoon, everyone. See you later.